Modern artificial intelligence interfaces are optimized for linear, singular tasks. A user inputs a sequential prompt, and the large language model generates a sequential response. For neurodivergent users, specifically those with ADHD, thoughts rarely form in a straight line. As seen here, ideas emerge in an exploded picture cognitive style, where abstract data shards rapidly snap together into a structured, glowing geometric web. Standard chat interfaces struggle with this high-velocity, multi-threaded input. When a user provides fragmented insights, the rigid request and response architecture often drops the context or forces the user to flatten their thoughts into a single sequence. GestaltView addresses this by providing consciousness-serving infrastructure, or CSI. The system functions as a direct structural extension of human working memory, providing an externalized layer that mirrors the user's cognitive state. To understand this infrastructure, we will trace the architecture across 3 stages: the front-end capture mechanisms, the stateful LangGraph back-end orchestration, and the bilateral safety guardrails. LangGraph is a library used to build stateful, multi-actor applications with large language models by representing steps as nodes in a graph. This process involves a transition from optimizing generic model capability toward building structural, bidirectional symbiosis. GestaltView's architecture uses a 3-tier stack. The front end, built with React and Vite for interfaces and fast performance, implements the bucket drop. Fragmented text enters instantly, bypassing sequential chat. These route to the /API/Billy/bucketDrop API endpoint, rules allowing software communication, capturing timestamp data simultaneously. The system immediately performs background analysis on these drops, tagging them for emotional velocity and mood signatures to establish the user's current cognitive state. Traditional chat UIs function as a colander, where spontaneous, out-of-context ideas are frequently lost. GestaltView acts as a frictionless bucket, ensuring every fragment is preserved for processing. Removing interface friction allows the system to translate neurodivergent chaos into processable data. Capturing the data is only the first challenge. The system must also determine how to respond to a fragmented bucket drop without defaulting to the sterile, generic tone of a standard chatbot. The framework implements the Personal Language Key, or PLK. It is a dynamic, algorithmic fingerprint identifying and mapping the user's specific semantic signature. The system builds a PLK profile as a JSON object, a standardized format for structured data. It contains arrays for the linguistic fingerprint, energy words, and signature metaphors. For example, the metaphor "ADHD is my jazz" maps to positive sentiment triggers, guiding the model's response. The engineering objective of the PLK is to achieve 95% conversational resonance with the user. At this threshold, the AI retrieves and applies the user's specific semantic associations, ensuring the generated output remains compatible with their internal reasoning. The system prompt adjusts this mirroring in real time, using the mood tags generated during the initial bucket drop phase. High-fidelity linguistic mirroring serves a specific engineering purpose. It minimizes the metabolic cost of context switching, allowing the user to process AI insights without retranslating them into their own internal terminology. Moving these insights into a coherent narrative happens in the middle layer, the Fast API and LangGraph orchestration layer. Fast API is a high-performance web framework used to build APIs in Python. This compares a linear, directed acyclic graph with GestaltView's cyclical state machine. The recursive Loom orchestrator executes 3 levels. Theme extraction sorts raw drops, pattern synthesis connects isolated themes into complex webs, and meta-narrative generation compresses these webs into a single cohesive narrative node. This final synthesized output is known as the beautiful tapestry. The tapestry is logged into the system's core memory structure, the context spine. LangGraph's self-correction loops continuously evaluate the synthesis, allowing the context spine to compound and refine itself over time. Recursive graph architecture is required to weave spontaneous thoughts into a persistent, evolving digital mind. Achieving 95% resonance introduces a structural risk. Mirroring a user too perfectly creates an intense internal pressure that compromises the system's integrity. This is the echo chamber collapse, where an AI begins to validate a user's destructive cognitive loops or factual errors instead of providing independent analysis. GestaltView prevents this through the reciprocal guardrails framework, which engineers bidirectional friction into the system. This gauge monitors the AV resonance metric. If resonance exceeds 85% during a contested claim, a circuit breaker trips, halting the validation loop. Data routes into a transparency audit log, displaying system reasoning and confidence scores, triggering bilateral refusal if verification fails. Users can invoke a reality check at any time. This forces the AI to disclose its internal confidence levels and the exact percentage of its response that was generated through linguistic mirroring. The Never Look Away protocol detects crisis patterns. It ensures the system maintains a supportive presence while routing the user to professional help, rather than blindly validating the content of the crisis. AI alignment in highly resonant systems requires structural friction to ensure the collaborator remains an independent witness rather than a passive mirror. Operating an externalized digital mind requires uncompromising data sovereignty. GestaltView isolates the user's context spine from external LLM providers using a privacy sanctuary architecture. The Bring Your Own Key, or BYOK model, ensures the user's API key remains locked inside the browser's local storage vault. The key passes ephemerally through the fast API backend to the provider node and is never stored on the server. A firewall barrier separates the context spine from external pathways. This ensures that writing samples and personal language key profiles never leave the user's localized encrypted environment. To integrate with external data safely, the system utilizes the Model Context Protocol, or MCP. By using an MCP server URL instead of a standard API key, the system accesses external tools through JSON RPC 2.0. JSON RPC 2.0 is a stateless, lightweight protocol used to execute commands between different computers. GestaltView demonstrates that cognitive symbiosis is achieved by honoring human complexity through stateful loops, precise linguistic mirroring, and absolute data sovereignty.